Okay, so to repeat again, Aubin Geoffre from École Saint-Étienne will have a talk today. Aubin, the virtual floor is yours. Please go ahead.
Yeah, okay. So thank you for the invitation first. So I'm Aubin Geoffre. I'm last year PhD student in Saint-Étienne. I'm supervised by Julien Bruchon, Sylvain Drapier, and Nicolas Moulin. And about the topic of my work, I'm working on the upscaling on flows within fibrous media. So, and I use a statistical approach for this problem. That's why I've used various data science methods, including a machine learning technique that I'm going to present today. So this technique is basically a Gaussian process regression with the use of anisotropic kernel. So we have used this technique for feature selection, and we have collaborated in this work with Rodolphe Leriche that will be cited here. So here's the plan of my presentation. Apparently there is a wide audience, so I will first discuss about my problem to see why we have considered this technique. Then I will try to be quite general about the mathematical grounding, just for you to see if this technique can be useful in your applications. And at last, I will show some example to illustrate my talk, including the one I've studied during my PhD. So basically, our team is trying to model direct manufacturing processes for composite materials. So the composite materials under consideration is basically a combination of an epoxy resin, that is the matrix, and a carbon fiber reinforcement. So you can encounter such parts in aeronautics, in automotive industry, and so on. So there are plenty of ways to manufacture such parts, but we are here considering direct manufacturing processes in which the resin is liquid at first state, and this resin will fill the fiber structure that is initially dry. So as you can see in the photos, we can observe a flow within a fibrous structure. So if we take a closer look at the fibrous structure, so here is what we can see experimentally. Then we can see a complex fibrous arrangement that led us to consider a stochastic modeling. So we have tried to mimic those fibrous structure with a code called Mignus, and this code allows us to generate randomly some fibrous microstructure. Here is an example, and those structures has been found to be representative to the experimental one. So once we have this fibrous structure, we need to characterize their geometry. So we need to characterize the pore structure, the geometry. So we have identified several morphological descriptors, starting from a really simple one, such as the number of fibers or the fiber volume ratio, to more complex ones, such as nearest neighbor distance or Delaunay triangulation characteristics. So in the end, for each of for a given geometry, we have 28 morphological descriptors to characterize the pore structure. So once we have this complex fiber structure, we need to analyze the flow within them. So for that, we use a permeability that is basically the ability of the porous structure to be crossed by a fluid. So it directly depends on the pore structure. For example, if the pore structure is really tortuous, then the permeability will decrease. So in the end, permeability has to be considered as a function of the morphological descriptors that I have introduced before. To compute this permeability, we perform flow simulation within a finite element framework that is based on the in-house implementation. So by post-processing the results, we can retrieve permeability. So in the end, we have basically an input dataset that corresponds to our feature, and it is made with the morphological descriptors vector for each of the, let's say, n volumes under consideration. So that's the red box. And on the other end, we have an output dataset that is composed of permeability. So the question starting from this data is basically which morphological parameters provide the best statistical description of permeability, and how to build a predictive model from them. So in machine learning, let's say, vocabulary, it's basically a problem. The first question is a problem of supervised feature selection. So which subset is the best to describe an output? And the second question is a typical regression problem. In addition, we have some constraints. For example, we can have a correlation between the features. For example, if we have a high number of fibers, then the distance between neighbors will decrease, and so on. So we have basically a correlation between features. We have a potential non-linear relation between the inputs and the outputs. We have also some variability and small data set because the data are quite expensive to obtain. So in the end, the problem that I'm describing here is quite general and can be encountered in several applications, such as biomechanics or material science and so on. So I will try to describe them, to give an overview of supervised feature selection techniques, and then I will explain the selected technique. So if we look at the literature about supervised feature selection, then we can find three main methods for such problems. So filter methods, wrapper methods, and embedded methods. So filter methods is basically analyzes the intrinsic properties of the dataset, such as distance or correlation. So here we can find a chi-square test or ANOVA and so on. The wrapper methods are quite different because they are used like a learning method, an additional learning method, and the idea is to build the relevant feature subset as the one that optimize performance of the model we have chosen. So for example, we can use a classifier and we analyze the performance of the classifier depending on the subset we have chosen. And at last, and it's the technique under consideration here, we have embedded methods that gather both of the advantages of these methods, in the sense that the training of these methods directly give feature selection. So here we can find a decision tree, but also a penalization regression, such as a lasso or ridge regression. So, which is basically a least square method under some constraint. So here, it's these methods are quite close to the one we are describing here. We are focused on Gaussian process regression, that is kernel-based Bayesian regression. So at first it's used for regression, but it turns out that we can use it also for feature selection. And I will explain it now. So actually, this technique is not new. It can be found in several other work, but we have it's the first time we have used it in our community. So I don't know if you are familiar with Bayesian regression, Bayesian modeling. So I've decided to go from the start, explaining the mathematical groundings of that. So I think I will skip this slide for going into this one. So the problem of Bayesian regression is the following. So we start from a data set composed of XY couple, and we assume that there is a function that allows to go from X to Y. It's basically our model. The question is that if I take a new input that doesn't belong to the data set, X star, what will be the most probable outputs and with which uncertainty? So in Bayesian framework, we use a probabilistic approach for that, in which we will try to assess the probability of the model knowing the data. This is what we call a posterior distribution. That's the thing we want to assess. And through Bayes' formula, this can be expressed as a product of a probability over the model, that is the prior, times the probability of the data knowing the model. It's the likelihood. What is very central is the prior, because it's basically an assumption we have to make on the behavior of the data. So it's basically the most decisive the most decisive choice, modeling choice in this context. So I will explain. So in this context, the assumption of the prior distribution we make is the following. So, in other words, it's the assumption of the model without the data. So we doesn't consider the data yet. It's only the models without the data. So we are making the assumptions that these models follow a Gaussian process. So here it is. This Gaussian process has a mean constant that is set as 0. I will explain why. Actually, the mean value is not really relevant, so we can set it at 0. And it's defined with a covariance function, k. I will explain it a bit later. So if we go back to the Gaussian process definition, this means that for any subset I can take from fx1 to fxn, the following vector will follow a multivariate Gaussian. So I've tried to illustrate it with a small example. So if fx1 and fx2 follows a Gaussian process, then we can see that. So basically, the first column describes a low covariance. So the off-diagonal terms are quite low, and here the diagonal terms are higher. So basically, I won't dive into much details, but what you have to see is that the diagonal terms correspond to the variance. So basically, the amplitude of the points of the function, and and the off-diagonal term will correspond to a covariance. So basically, the interaction of both points. If the interaction, so the covariance, is high, then the values of these points will be close to each other. So in the end, the curve will be smooth. So basically, what I'm trying to explain here is that the covariance kernel basically controls the smoothness of the function and how a point interacts with each other. So this example can be enlarged in a continuum case with the use of kernel K. That is basically a symmetric semi-definite positive function. That basically is a function of the distance of two given points. So the idea is that the larger the distance between points, the lower their interaction. So, as I said before, choosing a kernel is basically making an assumption of the smoothness of the models. So it's a really decisive choice. I'll try to illustrate that with an example. So here is a function that follows a Gaussian process centered on 0 with some random some kernel. Sorry. So here the three curves are basically samples from this Gaussian process. It's what we call the trajectory sometimes. So what we can see is that if x equals x prime, then we retrieve basically the amplitude of the curve, that is the diagonal here. And then for when x is not equal to x prime, then the interaction between those points will be expressed with once again the kernel function. So here we have a low interaction between those points, as those points are quite remote from each other. So here are three samples, but if I increase the number of the sample, then I will retrieve basically the gray distribution. So 0 mean and a dispersion following the gray curve. So there's plenty of kernel function that you can use, and the main differences between all of them is how differentiable they are. The most common one is the RBF kernel. So it's basically a squared exponential that has the particularity to be infinity differentiable. So the behavior will be very smooth. But then you can find also other kernels that are less smooth, such as Matern, that allows us to enlarge, generalize a lot of kernels. For example, here is a Matern kernel that is one-shot differentiable, and also exponential kernel that is not differentiable. So what is interesting to notice here is that the smoothness of the models, and we can see that in the end, the modeling we will retrieve will depend a lot on the kernel we have chosen. Until now, we have only considered the models without the data. So now we will incorporate the data into the strategy, and we will try to assess the posterior distribution, so the model knowing the data. We are forcing the models to pass through all the data. So it's what we call a conditional Gaussian process. So what is under consideration here is basically the value of the model in a given point, knowing that forcing the models to be equal at the data at the known point. So if we constrain the models to go from to pass through all the data, then you have these graphs. So you can see various samples from constraints to pass from the data. And if we increase the number of data, then you have a more precise model, naturally. What is interesting to see here is that if you increase the number of samples, then you can have a mean trend, so basically the blue curve, and some kind of dispersion that is the uncertainty. In the context of Gaussian process regression, we can express this analytically. It turns out that the probability of this, so the probability of the model at a given input, knowing the constraints, forcing the models to pass to pass through the data. This follows Gaussian law. So we have to imagine here a Gaussian distribution. And from this Gaussian distribution, the mean value and standard deviation can be expressed really easily with this formula. So in the end, this is a quite easy to implement, let's say, regression methods that both allows us to know the most probable outputs as well as the uncertainty. So it's kind of interesting. But the problem is that if I go back to the kernel, so the kernel is very central in the modeling, but they are defined with two parameters, sigma and L, that are the hyperparameters of our model. So sigma is not really significant here. It's basically the amplitude of the model. What is more interesting is the length scale or correlation length L that express the decay of the covariance. So basically, what is the characteristic the characteristic length for the interaction of points? So as you can see, choosing different length scale have a huge impact on the model. So if you have a low L, then the points doesn't really covariate, and the behavior is kind of noisy, let's say. But if the L is higher, then you have like a smooth curve, as I explained before. So the question is how to choose these parameters to be consistent in the modeling. This is usually made with an optimization procedure in which we are maximizing the marginal likelihood. So I won't dive into much details, but marginal likelihood is basically the probability of the knowing output, knowing the knowing input. So we are trying to maximize this function. Here we take the logarithm because it's at first a product, so it's easier to use the log. So here is an example of a two given length scale, and here is the optimal value. So it's interesting to notice that it's not the value that optimizes the result, but it is the L value that is consistent with the maximization with this criterion. The problem now is that in the example I have showed, the kernels are defined with only two hyperparameters. So if we look at this means that there is only one correlation length for all the data. This is equivalent to assume isotropy in the sense that the same behavior is assumed along all of the n direction. And this is not really observed in practice because some direction can have a larger weight than the other direction. So this has to be taken into account, and that's why we introduced anisotropic kernel. So anisotropic kernel is basically a developed version of the isotropic one, and anisotropic kernel have a length scale for all of the direction we are considering. So, for example, here, Li measures how correlated to the output direction I is. So it's really interesting because it allows us to define a weight of direction I with respect to the outputs. So we have defined here the weight associated with direction I like that. And from that, by comparing the weight of all the features, we can perform feature selection. So it's interesting because at first we have a regression technique, but we can use the tuning of these parameters as a feature selection tool. The last thing I will talk about before showing the example is the problem of overfitting. Because, as I said, we are forcing the models to pass through all the data. So this leads to overfitting, and plus you can have noisy data. So this is a problem. For example, it's basically here a square function with a low noise, and we can see that the predictions are quite terrible. So the idea is to add some flexibility, adding a noise just to add flexibility and to prevent from overfitting. So I won't dive into much details, but this basically adds a noise in the KXX that is a matrix called a Gram matrix. It's basically add like one term, this term, in the formulation. So it's quite easy to take this into account. So now, if I sum up a bit, I've shown these techniques for both regression and feature selection, and I will try to illustrate it with some example. So I have three examples. The first is a design case just to see how this behaves in practice. The second one is a real-world application from some dataset, and the last one is the example I've chosen in my PhD. So here is a design case I have used. So basically what is important is that these are the same constraints as the original problem. So I've introduced three input variables, x1, x2, x3, on a uniform distribution. X4 is basically, I introduced X4 as a nonlinear correlated with X1. So it's basically here the square root of X1. So we have a nonlinear correlation with some noise. And at last, I also introduced an output that is nonlinear correlated with some of the features. And it's interesting to see that X3 is totally independent from the output. So I have chosen a noisy data with a rather small data set, only composed of 100 samples. About the modeling, we have chosen RBF kernel with the decomposition between train set and test set as a 90 train percent. So basically, the results we have observing here are the following. For feature selection, we retrieve that X1 has a bigger weight, as the biggest weight, and then X2. And it's interesting that we retrieve a weight close to 0 for both X3 and X4. That was expected in this example. So we perform a good, let's say, a feature selection that we are expecting. So, considering the regression, we can predict the results with a low error. So if we compare the test data to the mean of the Gaussian process regression, we have an error around 7%, and all of the data lies within the confidence interval. So we can see here in this design case that we have satisfactory result. Then I've applied this technique to a real-world data set with the high variability. So I've used California housing dataset from scikit-learn. So it's basically a dataset with some features that is the latitude, longitude of some house, and the output is the median house value. So what is interesting here is that we have a kind of high variability, as you can see here, and we have a huge data set. So this data set has been reduced to only 1,000 data, because I will explain why later. So once again, we have chosen a RBF kernel with a division between train and test 80 and 20. So we have found that there was a huge dependency on feature selection on the noise intensity. So we have decided to set this noise intensity as the one that minimizes the error between the test data and the mean prediction. So here is the assumption we have made. It's kind of questionable somehow, but we've decided to set it like this. So in this, here are the results. So for feature selection, we can see the dominant features as the latitude, longitude, and then the median income. And it's interesting because those results can be compared with ridge regression one, because actually this data set is used for as an example data set. So other people have analyzed it, and our results are consistent with the other one. Considering the regression, we can predict really thoroughly the price of the house with like an error inferior to 15%. And moreover, 85% of the data lies within the confidence interval. So once again, we have a really powerful tool for both feature selection and regression. And at last, I will get back to the initial problem. So if I recall, our problem is basically we have some input feature that characterize a fiber structure. So here is the fiber density, the nearest neighbor distance value, etc. And we have an input data set that is the permeability, and we have taken the logarithm of the permeability. We have similar choices for the modeling, and once again, we are setting the noise intensity to minimize the error between the test function and the mean, the test data and the mean prediction. So with the same methodology, we have those results. So it appears that VF is the fraction of fiber. It's the dominant feature with respect to the permeability, which is in line with literature. And we also find that the delta 3, that is the mean distance to the third neighbor, is has also an impact, which is more surprising, but it's close to some results that we find in the literature. In the end, we have concerning the regression, we can predict the permeability with really low error, and all the test data lies in the confidence interval. But if we discuss a bit more about the data sets, we can see that maybe this Gaussian process technique is too much in the case of this example, because here's a representation of our data set, and it turns out that all the features are highly correlated with each other, and they are only correlated with the output too. And linear behaviors with kind of low variability is observed. So this means that actually any feature can be selected to precise to describe precisely permeability. So that's what we did, and we have chosen VF. That is the most straightforward, let's say, parameters. We have chosen these parameters to describe permeability. So this study between permeability and morphological parameters is described in an article published in 2021. This article used Gaussian process regression, but also other data science techniques such as Kolmogorov test to investigate the relation between morphology and permeability. So we are mainly focused on geometrical sensibility, so particularly the influence of reduced randomness. We also characterize isotropy and so on. And on one end, and in the other end, we have analyzed the interface condition sensibility. So in the end, this gives a general probabilistic model that allows us to characterize the probability distribution of permeability. So here is our main results that you can find in this article. So in the end, if I go to the conclusions, I have shown Gaussian process regression techniques as an embedded method for supervised feature selection. So this is a kernel-based Bayesian method that's based on the Gaussian prior. The hyperparameters are computed with the maximization of likelihood. But also the noise has been fitted to minimize the relative error between our test dataset and the GPR mean. So in the end, we have both performing method for regression and feature selection. So the advantages of this method is that it's really suitable for small datasets, and as you can see, the formulas are quite simple, so it is easy to implement and versatile. But on the other hand, it has some drawbacks. The gram matrix can be this is not a sparse matrix, so it can be really time-consuming and time and space-consuming to invert it. So it's not appropriate for large datasets. And we also have found a noise sensibility that we are addressed here by minimizing the error, but maybe we can think to other techniques to fix it. Okay, so yeah, here it is for my talk.
Thank you, Aubin, for a very good presentation that gave us insights into the really methodology that you have used, and with a number of nice examples that illustrated the methodology. I'm really grateful that you did this work for us. I'm opening the discussion now, so whoever wants to ask a question, just switch on your mic. You can switch on your camera as well. And yes, and please go ahead.
Can I go ahead first?
Sure, Sarab.
Hey, thanks for the talk. It was really nice and clear. You very much explained the drawback that it's not a suitable method for large data set for the very reason that you have to invert matrix, and plus you bring the non-symmetry into the prospect of these gram matrix also because of anisotropic kernels. So how do you actually do that? I saw that on 20th slide that you said that you reduce from 20,000 to 1,000 samples, and how do you exactly do that?
As I said, the technique is not really appropriate for large data sets because if you take, for example, the tuning of parameters or the mean prediction, this basically relies on the inversion of this matrix. So and this matrix is not sparse because, as you can see here, especially in the anisotropic case, you can have you don't have like zero metrics such as, I don't know, finance, zero terms such as finance method and so on. So I have forced to reduce this data set. Actually, I don't know if I know that Gaussian process regression is really suitable for small data set, but I don't know if there are some methods to tackle such kind of issues. So here I've simply reduced the data set, but maybe there is other techniques for doing that to simplify this. Maybe with using some kernels. Then I know that there is some kernels that you can have that is a zero if the points are sufficiently remote. So maybe it's a technique to simplify the matrix and this inversion just to perform like bigger data set. But here you're right. I reduced this data set just to prevent this problem.
But so you basically only consider 1,000 points out of this 20,000? That's what you mean?
Yeah, that's what I mean.
Okay. Okay. And the second question is, can you go to the slide where you added the noise alpha to the kernel also? I guess previously, this is, I did not. So how do you, can you intuitively explain this ninth equation maybe?
I'm sorry, what do you want me to explain?
I did not understand the ninth equation, that how it exactly helps.
Okay, so here is kxx is basically corresponds to the variance in the data. So if you not putting any noise, then your Gaussian process is forced to go to pass through all the data. So what this adds is just a flexibility on this data.
But you're only adding this noise to the diagonal entries.
Yeah. Actually, you can define in the broader case. You can define a noise intensity for any sample you had. But here in the example, I used basically one noise for all the Gaussian process. But you can define a noise that depends on the samples.
Okay, so, thank you. Yeah, I have some more questions. Maybe I'll go through presentation again and write to you if that's okay.
Okay.
Thank you.
Aubin, here's Anas. Thank you very much for the nice presentation. I'm really looking forward for our third round where we can talk more in details. I have some questions regarding the presentation, but we can talk about them maybe Thursday or next week, depends on your availability. Also, I was texting with Stefan. He also would like to be there in the last interview where we can ask you some questions about your future plans, your strategy for the project, and so on.
Okay.
Thanks a lot.
So may I ask a question about the size of the input, not the amount of data, but the number of features.
Okay.
How the technique, the kernel-based Gaussian process regression, perform when you increase the number of assumed features.
Yeah.
Which is your input, right?
Yeah, it's a good question. Actually, you will have the same problem because your gram matrix will increase and it will be more difficult to invert it. Actually, when let's say thousands of features are considered, those embedded methods are not really used. It's more like the feature methods are preferred because you basically don't have any training models to use, so it's basically using the correlation. But if you have, let's say, a number of features that acceptable, then you can find Gaussian processes. Then you can use Gaussian processes or any embedded method. But yeah, you're right. When your number of features increase, then these techniques are not really suitable unless you have found some method, as we discussed earlier, to simplify the matrix.
Mm-hmm. And let's say that because if you are restricted to the number of features, probably you need to have some expert that selects the features in the first place, meaning that you have, let's say, your full field data, all the alignments of the fibers, which is a large image, one can say, and then you want to assess a set of features that describes you this particular case. But it doesn't need to always be accurate and correct, the selection of the features themselves. And do you have any idea whether your modeling technique can detect such case that, let's say, there is a number of elements in your data sets that cannot be easily modeled with this particular regression based on these features? And is it possible to detect this problematic data part of the data set and, let's say, try to figure out a new feature that will represent them better?
Okay, I'm not sure that I understand well the question. The question is basically if you have some feature that's really noisy or that are poorly correlated with the outputs?
I mean that maybe one feature is missing from the
one feature is missing
that represents, let's say, partially part of your data set, represents the correlation between the input and output. Let's say if the feature is missing, your model probably will be inaccurate. It will be higher.
Yeah, in the case we have studied, we don't have missing data, so I don't know how it is used in practice, because yeah, sure, it will affect the whole modeling, because you have to know basically, yeah, for constructing the matrix, you have to know you can't have any missing data. So actually, to be honest, I don't really know how this is processed, because it's out of the context of the work I described. So to be honest, I don't really know how this is adjusted.
All right. Thank you for the answer. I can see there are two raised hands. So please, whoever wants to talk first, maybe Hussein first, then Atul. Hussein? We cannot hear you. Okay, so maybe Atul?
Hi, am I audible?
Okay, yes, we can hear you.
Yeah, thank you. So my question was basically about two things. One is regarding the kernel. In all of your examples, you have always chosen RBF kernel. So is there a specific reason of why that was the case, or have you explored a combination of different kernels and other kernels that are available? And the second question is regarding the features. If you are trying to pick up the important features in your model, how is it any different from a sensitivity analysis?
Okay, regarding the kernel, you're right. RBF is like a questionable choice, especially when you have a really noisy data set. For example, in the California housing, I think using RBF kernel is not a really relevant choice. We have used it because it was like more simple, but yeah, if you want to tune it really thoroughly, your methods, then you can try the other kernel. It was just here for the example. And yeah, you can also use design kernel. I know that Rodolphe Fleurich is doing that, for example, with physics-based design kernel. So it's also a way yeah, it's a way in the Gaussian process regression. You're right. Okay, so this was for the first question. The second question was basically on the difference between sensitivity analysis. Okay, so we have tried to we have explored this method, for example, Sobol indices. I don't know if you refer to that. And it turns out that the features has to be independent. That is not the case here because we don't have really control in the end of our fiber structure. We can't act on them separate independently. So it was a drawback, and plus it can be difficult the Sobol indices are quite difficult to compute, so that's why we have preferred this method. But we have explored this. This method. You're right.
Hey, Jakub, do you hear me now?
Yes, Hussein, please.
Okay, good. Can I ask 2 questions?
Sure.
So the first one is that your third example is kind of like in a domain which is completely fixed, right? It's not infinite dimensional domain. Am I right? It doesn't go from infinity to infinity.
Yeah.
So when you did work on your kernels, did you check if you change your kernel, your hyperparameters converge or not? And I mean, if you change your mesh size, basically regression mesh size.
Okay. As I said before, we have chosen RBF kernel just to illustrate, basically, just to illustrate this technique. I know from the example that I have tested that changing the kernel will have like an influence, but if it's what I mean is that if you want to tune your modeling like really thoroughly, you can try other kernels maybe. We just use the RBF kernel to simplicity sake, and actually our results are quite good in comparison with.
What my question is that when you make your data more, like you make your matrix more denser, let's say.
Okay.
Does your hyperparameter still act asymptotically or not?
The hyperparameter depends on the noise intensity.
Okay.
And that's why we have it's really sensitive to noise intensity, and that's why we have chosen the noise
That's
intensity.
probably why RBF is not good choice for this, because it shouldn't. And that's and the second question that I have is that did you use direct inversion? I mean, did you implement it like a direct inversion in your, because you have quite a bit of data, right? You have about 20,000 data sets in one of the examples.
No, we didn't focus on like a matrix inversion. Maybe it's a way, as I said before, to maybe go further and to to consider like bigger data sets. But in our example, a constraint we had is that we had a small data set because each of the data, considering the fiber structures and the flow simulations, are quite expensive. So we didn't go further in terms of matrix inversion. But yes, of course, you can improve it. For example, I'm also working on finite element modeling, and the matrix to invert are way bigger. So I think, of course, there are some methods to accelerate this procedure. But here we had the constraint of small data set. That's why we only consider simple inversion.
Okay. Thank you.
Stefan Bordas, you raised your hand. Right.
Thank you. Thank you very much, Alban, for the presentation. It was really very nice. Can you go back to the parameters you used to describe the microstructure, please? And we'll talk again on Thursday. So I just want to understand something.
Yeah, here it is.
Yeah, something like that. Okay, 28 morphological descriptors. So my question is, how do you somehow assess whether these 28, let's say, are minimum in terms of that they are sufficient, that they are both necessary and sufficient, more or less, that they form a basis of the descriptor space that you want to do? I guess this is the whole point of the work you're doing, right? To try to figure out if using 29 would be too many and using 27 would be too few, right? Something. I guess this is one of the questions you're trying to address, because if the fewer you have, the easier it is to generate the statistical space, and at the same time, you don't want too few to be able to then miss information. And I'm interested in knowing what is the process that you use to figure out whether this is a good choice, a bad choice, a best choice, an optimal choice, suboptimal. You know what I mean?
Yeah. So basically, considering the literature, we usually such a number of features are not considered for fiber structure. It's like only maybe 3 or 4. So here, making 28 features is like bigger than what we find in literature. And for example, most of the model we encounter in practice are only based on one parameter. That is basically the fiber volume ratio. So we don't have the proof that this will form, for example, a base of the space. But we have seen that all the features are really correlated. Plus, the variability with respect to permeability was quite low for any of those morphological parameters. So this led us to consider that, okay, we can choose any of this one, it's okay. But yeah, you're right. Maybe we can considering the literature, 28 morphological descriptor are way more actually. To have kind of big to have a thorough description of the permeability. The idea of the study was just to know which one was the most relevant.
I see. Thanks. And because I'm asking myself, so beyond the fact that there are 28 to 50 or 100,000, I'm just thinking about what would be the procedure to define the minimum set of parameters for a given microstructure. For example, if we had another type of microstructure which we don't know, and that may not be as simple as the one you show on the picture, for example, a 3D micro CT scan of some real material that looks like a sponge, where you have interconnection, you have tortuosity of the channels, they have different widths and diameters and distances, and the connectivity is different, the fractal dimensions can play a role, and so on. So when you have a real microstructure, one of the difficulties, I think, is to select the minimum set of parameters. Like if you have a constitutive model for for tissue, for example, some people use Ogden and they add some terms in order to capture some more anisotropy, for example, or fiber slippage or whatever it is that they want to figure out. So they add parameters, and at some point, as you were saying, you can do some overfitting, and what you see is some mumbo jumbo, but you can't really figure out what is what in this thing. So in our case, and I think in many cases, you have very hugely complex geometries, but you maybe can boil it down to very few parameters. And my question would be, what is the procedure or the methodology that you would follow in order to identify these key parameters?
Okay, here we are. The situation is quite simple because the microstructure under consideration are basically a set of cylinders. So then you can easily, let's say, compute some morphological parameters such as nearest neighbor distance or Delaunay triangulation and so on. So it's kind of easy with this microstructure. But yes, you're right. If you're consider like 3D with I don't know, tortuosity and I don't know complex geometrical features, then it can be difficult to identify those kind of parameters. But it's not the problem of the modeling here. It's more the problem of the generation of data, I think. Here, what was simple is that our data was kind of easy to compute. But so here the modeling, so we have like a good base from then the modeling. But if you have like more complex, I don't know actually which morphological parameter can be suitable. I don't know. I think it depends, of course, on the geometry under consideration. So it's difficult to say anything without knowing the
No, clearly, I'm not also interested in the answer to the specific question, but more on the approach to find an answer to an event for an eventual unknown geometry. So what could we do? And I don't think there is an easy answer at all. I'm just throwing the question.
Stefan?
Yeah.
I can't get your question. Can you explain it again?
Yeah, so for now here we have a few morphological descriptors related to the geometry. So for example, we can make a Voronoi tessellation and a Delaunay triangulation that gives us the nearest neighbors, and it tells us how close together the cylinders are and what is the average distance and so on. So you can describe the geometrical and topological space using a few parameters. And because you have a complete control on the geometry, you see the cylinders have a specific radius. They are, you can control that quite easily. So then if you take a micro CT or any image of a microstructure that you look at, you will not have such a nicely packed set of cylinders. They may be looking completely differently, not be cylinders. They have variable diameters. They are all connected together, but you don't know exactly how connected they are. And, so you need to take a real microstructure and try to quantify which of these geometrical parameters are more important or less important than others.
I hardly think that in that case you can use, if you're, so basically you are doing a regression on this geometry, you mean?
I don't know if that's what I
mean. If you are doing that, I hardly think that this current kernels will work on those, right?
Yeah, I don't know. I'm more looking for.
I know it won't.
I'm sure you know, from a methodological point of view, how to actually do it. Because I was thinking,
well,
let's say if we wanted to generate, let's say that you have 100 samples, which would be really a miracle, of a real stuff, and you take 100 samples, and then you observe the geometry and then or topology or both, and then you try to figure out, okay, now I want to generate such a sample which is similar to the ones that I measured, but by hand, because I cannot have 100,000 samples, but I would need 100,000 samples maybe in order to be descriptive of the topological space. Yes, exactly.
Yeah. So the problem that you're mentioning is that, so if the geometry is different. So how are you going to describe the connection between the correlation between neighbors? That's the problem, right? Because if you can do that, then you basically can regenerate the system again.
Sorry, I didn't understand.
So if the way that I understood is that if the geometry is completely complex, how am I going to describe the connection between the points that I have if I discretize it into point-wise? And then if I find that connection, then I basically can regenerate the geometry and whatever the field is I want, right?
Yeah, that's it. Yeah.
Yeah. So the one major problem is that in those complex geometries, you don't have L2 norm anymore, right? And because it's not a flat space anymore.
You cannot compute using Euclidean distances, you mean?
Exactly. There is no Euclidean distance anymore.
Okay, but then you can maybe use some other measure.
So one of the things that maybe you can do, what we were discussing with Lars yesterday, is that probably you can do something similar to isogeometry that you do. So use NURBS to create very simple geometry and then identify randomness of parameters that describe that specific NURB. And then that's Euclidean, right? So you can play with it.
But you mean describe the geometry using NURBS?
Yes. Or whatever you want, right? It's kind of a regression and regression.
I think then I don't understand the previous remark on the L2 norm. Okay, well, maybe we should have this discussion somewhere else.
Yeah. If you have an extremely like curvature style thing, these kernels that you have won't regress anything, won't describe the correlation.
Yeah, I think the other problem, so there is a geometry problem for sure, but there is also a connectivity problem.
If you, yeah, that's also, well, if you want to look at from connectivity problem, actually you get rid of the geometry problem.
Yeah.
Because then you're looking at it from a matrix point of view.
I had to call at the same time. Can you still hear me?
Yeah.
Yeah. Yeah, because, maybe what I was thinking is one way would be to model the geometry using a set of pipes that are all connected together. And
pipes like regular pipes?
Yeah, just pipes, like piping system in a house.
Okay.
And because they have then intersections, they have, you can make them straight or curved. And then you model properly the connectivity and the tree structure, the graph structure that represents the microstructure, but you don't need to do a full 3D model of the whole thing, which is super complicated. And you can generate hundreds of thousands of these models.
Now, Stefan, you are muted. I don't know what happened. Stefan, you are muted. Okay.
Okay.
Stefan, I think your phone is muted.
He's going.
Probably he cannot hear anything as well.
I think Sohrab has a question. Probably he should ask now.
Yeah, but okay. Wait a second. I'm not sure.
Oh, I think he's still.
I texted him. Let's see how long it takes until he realizes.
Okay. Stefan, you are muted.
No, you're not. Reversed.
We cannot hear you, and probably you cannot hear us.
He left.
I think he
wants to reconnect
the meeting.
Okay, maybe meanwhile, I don't know, Sohrab, do you want to ask a question? We are.
I just have one comment to Hussein. Hussein, if you want, I can arrange some WebEx with you and show you the problem in hand and see what you think about it. Because it's a bit more complicated than that.
Okay.
Okay.
No problem. No problem.
I can send you Aubix whenever you want. And then
Yeah, no problem.
But maybe application of these autoencoders, you know, this compression, the compression techniques could help as well.
That's for
identify.
Kind of.
Yeah, but the encoder
reducing
decoder would help to regenerate the geometry that we have in hand. Like to have this multi-fidelity problem, like you start with a coarse and then you can create a more high fidelity one.
That's basically model reduction.
Yeah, yeah.
Or
so
representation.
practically you create this kind of cone. Let me open my...
Yeah. Okay. So I don't know. Sorry. Yeah.
Where am I? I'm here.
Anas.
Okay, we can discuss this cone idea later. Okay, it's fine. I think.
Sarah, did you want to ask a question or?
Yeah, if there is time, I would like to ask a question
there's
to
time
Aubin.
for one short question. Yes.
Okay, I have one question to Aubin and one to Hussein. To Aubin, I just wanted to ask, what's your exact regression problem there? You are doing regression from these 28 parameters to just the permeability, or is there something more than that?
Okay, so here the flow is supposed to be steady and with one phase. So yeah, basically what we want to predict is the permeability because it's an industrial issue in practice. But if you're assuming the flow to be multi-phase and transient, and it's the case I'm dealing with right now in my work, then you have multiple parameters to predict, such as capillary pressure or like porosity, void contents, for example. So then become more difficult. But here is like a simplified case in this the case I've presented.
So I suppose that the permeability usually should be positive, like even some other predictions that you want to make, some of them need to be positive, and then I guess you need to take care of some extra things. I'm not so sure, but I suppose Hussein knows about these capillary processes where you impose the constraint of being these values positive, output values positive.
Yeah. So one of the ways would be that you instead of using a Gaussian processes, you use Gaussian processes correlation structure, but you multiply it via you detach the marginal distributions from it, right? So you impose Gaussian process. If you impose, like, for example, beta process or Dirichlet process or whatever it is. So that could be one way. Another way would be actually locally constraining it. So there is a paper 2012. It's a French paper from University of Toulouse. It's a very good one. So in that you can see how you can constrain locally. Basically means that globally you have a Gaussian process, right? But locally you have a truncated Gaussian process, and that's basically very much simple thing to do. You just solve the Gaussian process problem, and then you truncate in the points that you want.
Okay.
And I have second question. Hussein, have you ever tried using, let's say, for large scale problems, Gaussian processes, but you reduce the problem size using the model order reduction method, like say TOD?
Well, I haven't, but I work on a small data set, so no, I haven't used on my papers. But right now I'm writing a paper which is actually doing that. It's kind of like low rank approximation style of thing. So basically you can use this spectral theorem, or the fact that you can write every function or matrix in terms of their expansion of their orthogonal functions or orthogonal components, right? Principal accesses, basically.
So can you comment on, do you have any general comment? Because you have two levels of approximation here. First is to reduce to smaller space, and then again regression on smaller space, and then projected back to the original.
Yeah, exactly. So, that's the way.
But can you comment on the accuracy of this approach? Because there are two levels of approximations.
No, I can't comment on approximation, on accuracy from that point of view, that if it's accurate or not. But one thing that I cannot comment on is that in general, low rank approximations have a well-defined norm. So you can, just abstractly speaking, if we are talking about a matrix, right, in a general point of view, and you want to make this matrix smaller from rank point of view, which means you can invert it easier and all those kind of things, you have a very well-defined norm for it. So you exactly know what's your error and all those kind of things. So, well, if you look at it from probabilistic point of view, you add some noise there, so you can compensate from practical point of view. So.
Okay, thanks. That's it from me. Thanks a lot, guys.
Yeah.
Okay, thank you very much again, Aubin, for your very nice presentation, and thank you all for a very deep and vivid discussion today. So I stop recording now.